I'm going to be talking about using big data, so a lot of data to um, get some awareness of post-fire debris flows. So my motivation here, I just want to be clear up front that this is pretty USA centric. So a lot of the applications you'll see is really centered on systems and places in the US, but I think you'll see there are broad applications elsewhere beyond that. Um, so let's just start with the basic fact that we know that rainfall thresholds are critical for landslide and debris flow early warning. And after major storms, you might want to see how well these thresholds performed. But if you've ever tried to pull lots of rain gauges to test a threshold for a large area, particularly in the United States, you'll encounter variable data formats, variable data recording intervals. You might have rain reporting out every 5 minutes. It might be once a day. Um, and this is because there are many different types of gauges that are used. And so trying to just get the data formatted so you can understand what happened can actually be a pretty heavy task. So my personal motivation for this is that back in 2020, there were some wildfires along the central coast of California, and there was a big atmospheric river storm that came in January and created several debris flows, created flooding. And the National Weather Service asked our research group how well the rainfall thresholds performed, if they needed to increase the rainfall threshold or lower it. And it took us an entire week to start to put the put the data together. Sorry, you're an echo. So if maybe somebody has their yeah, can mute their mic. Thanks. Um, so it took about a week for us to put these simple plots together to look and see if rainfall thresholds needed to be adjusted. Um, and that just seemed like too long to be able to get to a decision. And so we decided to create the software that we call Flow Alert. And so Flow Alert is a open source software that's available now through the USGS, and it's developed to query rain gauges to identify when and where storms cross a rainfall threshold so that people can make rapid decisions, so that you don't have to spend an entire week just trying to get data in the right format to look at it. And this is really focused on areas burned by wildfire. And I'll try and try and tie this together. Why burn areas in particular um, create a fairly well posed problem for just using rainfall as a threshold. So to do that, I want to get into the background of what connects wildfire to soils and hydrology. What does wildfire do? So let's start by just considering a forest that hasn't burned in a while. And just think about a raindrop falling from the sky in that forest. It falls from the sky. The first thing it might encounter are leaves and needles of trees. And then as it falls again from there, it might hit the forest floor where there's decaying leaves, litter, and duff. So that's the pathway of a raindrop for a normal forest. But now consider a burned forest. So here, all the leaves and needles have been burned off the trees. So that same raindrop would fall in this picture, and it's less likely to hit something on the way down. And then the forest floor here, you can kind of see that it's sort of a light gray. It almost looks like snow, but it's not snow. It's wood ash. So that raindrop is going to fall all the way down to the ground. It might encounter some ash, but there's very little litter, duff, decaying leaves on that forest floor, and so that water is more likely to run off. Um, there's another thing that happens pretty frequently in burn areas, which is fire-induced soil water repellency. So here, if you kind of look closely, you can see a water drop, and I place this water drop on the soil with an eyedropper, and it's been sitting there for 3 minutes, and it's beat up, and it's not going anywhere. And this is pretty typical of burned areas. So let me give you another example here. So here's a video where I'm just going to pour some water on the soil. This is in a burned area. So watch what happens. So you can see that the water just kind of pools up. It's not infiltrating very quickly. Um, it's very slowly going into the ground and mostly just running off when we pour water on there. The other thing that happens in burn areas is that whenever you heat soil above about 100 degrees C, um, the soil starts to lose cohesion because things like bacteria, fungi, fine roots, and even clays will lose their cohesiveness. Clays can swell up and crack and become uncohesive. So you can see my colleague here, is just pulling up this soil as if it's just kind of sand on the beach, not like a normal cohesive forest soil. Um, so all of those three things make it more likely that when it rains, you have runoff and you have erosion. And so let's just look at a video here. There it goes. So in these burn areas, when it starts to rain, you get runoff. That runoff incorporates often wood and sediment, and it can lead to these runoff generated debris flows where you have more than about 50% sediment concentration. See, there's a flush of wood. Here's another one. And it's hard to see, but if you look closely, you can see some larger particles being moved. There's a couple boulders in the foreground that are being moved by the flow. Um, so this is kind of a typical runoff generated debris flow. And just, I know that can look kind of like a muddy flood, but just to kind of show you some of the debris flow aspects, this is a house that's just upstream from where I showed the video. It's just a couple houses up the hill, and you can see it was clearly destroyed by debris flow. So sediment filled in the house, broke the walls. So this is kind of typical of a post-fire runoff generated debris flow. Um, and these kind of debris flows are unique. They're pretty different than say a shallow landslide initiated debris flow because there's no real headscarp. You might see rilling on hill slopes like you can see here, or channel incision like you see off to the left here. So these debris flows really start from a distributed runoff nature. They're not from a single landslide source. The other thing I just want to point out about these post-fire debris flows is that they are really global. So here's a map of places where we've seen post-fire debris flows around the world. So this is a study I did with some colleagues where we scoured the literature, and the size of each of those points on the map indicates the number of debris flows. And unfortunately, with climate change, in most of these areas, we expect to see post-fire debris flow activity increasing. So this really is a global phenomenon. So post-fire debris flows are not really reliant on soil saturation, as you can see. So the nice thing about that is we can really focus on rainfall alone as a predictor for potential post-fire debris flow in many areas. So to have this situational awareness of where debris flows might be happening, we need two ingredients. We need a reliable rainfall threshold, and we also need some rainfall observations. Um, so let's focus on the rainfall threshold first. And I'm going to show you how we get this from a product that we make at the USGS called the Post-Fire Debris Flow Hazard Assessment. We make about 50 to 100 of these per year, and it just depends on the number of fires. But we tend to make a lot, and we put it on the web. There's a map component to it that shows the likelihood of a debris flow, things like rainfall threshold, volume, and this sort of combined hazard metric. But to get the rainfall threshold, we use a logistic regression equation, and this is just an empirical equation. This is based on many observations of post-fire debris flows, and there are four components that go into it. So the first one is terrain steepness, and that's just the proportion of upslope area with moderate to high burn severity and slopes greater than 23 degrees. The second factor that we use is fire severity. So for this, we use a remote sensing product called the DMBR. That's the Delta Normalized Burn Ratio. It's really just a measure of how greenness changes before and after a burn. We also have soil properties. So here, throughout the United States, we have a product called the Statsco Soil Survey, and there's a measure of erodibility, which is the KF factor. We incorporate that into our equation. And then finally, the rainfall, how much it rains in a given period, 15 minutes, 30 minutes, or 60 minutes. And what's neat about this empirical equation is we can rearrange it to solve for rain. And if we assume a certain uh, probability or likelihood, we can come up with a rainfall threshold. So, for example, we often assume a 50% probability. So we want to know, okay, what's the rainfall that would give us a 50% probability of having a debris flow? And we recently tested this in a paper, and it worked pretty well for the first year after a fire. So that's how we get a rainfall threshold. And we calculate this. We have these maps, and we calculate it for entire catchments or these sub-catchments within a burn area, as well as individual channel segments. But really, practically, what people want to know is a single rainfall threshold for an entire wildfire area. So to do that, we develop what we call fire-wide threshold. So we get the rainfall threshold for all the catchments in a burn area. And we take the 50th percentile, and that gives us a rainfall threshold for the first year. And we do the same thing for the second year, but instead we use the 75th percentile. And the reason we do that is because in the second year after fire, we expect some recovery of the area. So we expect it to be less likely to have a debris flow. And what's nice is these are provided in a CSV. Like this table here, I just grabbed from a CSV file. That's an output from our hazard assessment. It's just on the web. And so I could easily pull these numbers. So 55 millimeters per hour is the 15-minute rainfall threshold for year one. Okay, so now that we have a rainfall threshold, we need to actually get some rainfall data. Um, and the first thing that you might ask is, well, why don't you just use radar? Because radar is, a proxy of the rain that you're seeing in your mountainous area. Well, the reason we don't use radar right now is because there seems to be a disconnect between the radar that's measured, 10,000 feet above the ground, and the radar and the rain that's measured at the ground surface. So here's a map from that's made by my colleague Andrew Graber. He and I are working on a project right now comparing rain gauges with radar. You can see in these text boxes near the water droplet markers, those indicate gauges. You can see the difference between the gauge recorded intensity and the radar recorded intensity, and they're pretty different. And there are good reasons that it makes sense that what's measured high up in the atmosphere isn't necessarily what's going to hit exactly underneath that pixel. So this is why we use rain gauges for our study. The way we get the rain gauge data is we use an API that's distributed by this company called Synoptic. So Synoptic is a private company, but we ended up using their API because we started by scraping web data from sites like where the National Weather Service has individual rain gauges on this Meso West site or from state areas like the state of California. But we found that basically Synoptic's a little bit easier to use, and researchers can use a free version of the Synoptic API with Flow Alert. So it ends up being a little bit easier just to use their tool to start to extract the raw data. So I want to walk you through the Flow Alert methods. So the first thing that we do is we start by pulling some boundary conditions. What's nice is all the hazard assessment data from our post-fire debris flows hazard assessments is on the web and is publicly available. So that makes it easy to scrape. Um, and we start by using by assigning a code, or excuse me, we start by grabbing a code that's assigned to each hazard assessment. And so the code has three letters, like in this case, HER, the three letters, and that stands for Hermit's Peak Calf Canyon. That's a wildfire. And then we have a year associated with it. So each fire has a unique code that we use to identify it. Um, then we grab a polygon of the fire from the hazard assessment, and we look for rain gauges within that polygon. So here's what that looks like practically. Here's a map. The red outline is the wildfire perimeter. And then what we're going to do is we take the bounding box of that perimeter, we extend it by 4 kilometers on all the sides, and then we search for all the gauges within that area. And so in this case, we found about 15. Um, and I'll show you what that looks like on the command line. Um, so here we go. It's really easy. So um, using this software, it's a one-liner. We just say poetry run flow alert and debris flow add HER 2022. So it's that code that represents the hazard assessment. It goes out to the web and it finds the shapefile of the fire perimeter and downloads that as well as the locations of the gauges. And so for this particular fire, it takes about 3 minutes to locate all of the gauges. I won't make you wait the entire 3 minutes for that to run. But what it returns is a list of gauges. So here we're interested in the ones that are active. That's what's highlighted. It also shows us inactive gauges, which potentially could be useful for historic data. But in this case, we're just interested in the active gauges. So we get 15 and we get important information like the latitude, longitude, elevation of where those are located. Um, and then the next step is to download the raw data. So now that we know where they are, we want to download the raw data. And again, this is just kind of a one-liner on a command line where we specify the fire with our code, HER 2022. We put in a start time and an end time. So the period we care about in this example is June to October. You can see in 15 seconds, it's run and it's given me the raw data for those gauges. And so what you're looking at here is the output from that. So this is the raw data. And there's actually all the weather data from the station comes with it. So we're only interested in precipitation in this case, and we use this column called precipitation intervals, which is basically just how much precipitation was recorded at a single at each time step. Um, but there are obviously other variables like wind speed, relative humidity, air temperature, things that you might care about, but we're not actually using those in flow alert. We're really focused on the rainfall part. And then the third and final step here is to calculate the rainfall intensity because for fires, at least, what we care about is the intensity of the rainfall, not necessarily um, the rainfall total, although we also calculate that. So again, this is another one-liner, and the main thing that goes into this command is the start and end time. Um, and you'll see as this runs, it outputs information where a rain gauge has crossed a rainfall threshold. So it tells us information like the time that a rainfall intensity crossed over the threshold, the intensity when it first crossed it, the intensity, the peak intensity, and then the intensity when it last crossed that threshold. And that only takes about a minute and 30 seconds to run. So this returns a table that has a lot of information in it, but importantly, it has the rainfall threshold here. So in this case, it's 29 millimeters an hour. It says if it was crossed or not. And then we have information like the total rainfall accumulation. We have the rainfall for each time step. And in this case, we actually calculate an intensity every 1 minute. Um, and so then we can look at the 15-minute intensity. So the time steps are 1 minute, but we're looking at 15. We can also look at 30 and 60 and then compare those against the thresholds. So we create these plots based on flow alerts. The plots are one of the outputs. And what we try to do is provide a lot of information really quickly on a plot. And so I'm going to walk you through what's on here because there's actually quite a bit. So we provide the name of the fire to make it kind of easy for people to recognize. Also, that fire ID, so people can link that to the hazard assessment, the state in the United States where the fire was, the gauge station ID, and the source, because these rain gauges that we're pulling from, they're not owned by the U.S. Geological Survey. So we kind of want to know, well, who owns this gauge? So in this case, the owner is HADS. Um, and in terms of thresholds, on a plot, we plot these dashed lines that show the rainfall thresholds visually. But we also have a table of thresholds, and we provide these in various units because um, we find that people that we work with like different types of units. So we provide it in millimeters per hour, inches per hour, or inches in 15 minutes, inches in 30 minutes, and inches in 60 minutes. Our partners of the Weather Service tend to use the inches in a certain duration of time. Um, we also have some checks to look for potentially anomalous data. So in this case, we're flagging data where we saw a really quick spike. So in this case, it increased by about 9 times in intensity over a 90-minute period. We found that that's sort of a good rule of thumb that that might indicate something's going on. It doesn't necessarily indicate the data is wrong, but it just alerts us to look more deeply at the data. Um, we also have this bar along the bottom that shows the recurrence interval. And so if you look at the color bar on the right side, that shows the recurrence interval in years for the 15-minute intensity. And so this is a way to also double check the data to say, oh, if something is 1,000-year event or 100-year event, just double check that there's not something going on with the gauge that might be wrong. So in this case, it mostly looks like 1 year. If you look really closely, you can see color changes. One of these spikes is it's in the 1 to 2 year range, but this all looks fairly normal. So as I've shown you, you can run Flow Alert on a personal computer, but we also run this on a Linux server, and this is where this is the big data part from my title. Um, so the way that we do this typically is we run every 2 hours. We run all of the gauges within all of the hazard assessments that we've had over the past 4 years. So at this point, every 2 hours, we are collecting data from 2,500 rain gauges and processing it. And then we're uploading that data to a dashboard so we can kind of visually see what's happening. We also have an email alert system. So an email is sent if a threshold is crossed to kind of say, hey, pay attention, there may have been some activity. So here's a quick look at our dashboard. So this is a map dashboard. And what you're looking at in terms of symbols is there are green symbols that indicate gauges that have recently had rainfall. And then there are blue symbols that are gauges where it's gone across a threshold. So if I zoom in and I select one of those blue gauges, when I click on it, it pops up, says, hey, this is the Three Peaks gauge. It was in the Dolan fire. There's some plots off to the right, and if I click on one of the plots, it'll pop up, and I can see that plot that I was telling you about. So the idea with this dashboard is it's just a quick way to have a snapshot of what's going on across the Western United States to know where we might have issues and what to pay attention to. And like I said, here's the email alert. So this is an example of an email that I got saying, hey, there was rain across a threshold. There are plots attached if we want to look at those plots. And then there's information about the time and the rate of the rainfall intensity. And we even build in a few things like this. Here we're saying, hey, this intensity is about 100-year recurrence interval. So maybe take a second look at it. Maybe that's not right. So we're trying to build in checks so that we can get a better feel for if rain gauge data is correct or if it's potentially just a gauge malfunctioning. Okay, so using the rainfall threshold and the rainfall data, we know where thresholds are crossed, and we can be a lot more situationally aware. Um, but there's an added bonus that this also allows researchers to quickly analyze data rather than just spending time processing it. So, like I said, that was kind of some of the motivation of this research. So here's an example of this is the Blue 2 fire, which is a fire that happened in New Mexico this year. Um, Rainfall in this area led to some debris flows and flooding in the town of Ruidoso. But I took this gauge and I wanted to quickly summarize what happened in this area. And so what this table is showing is actually I took all the storms that are calculated in Flow Alert, and this is indicated by the storm ID, which is the first column. And so you can see there are individual storms, 0, 1, 2, 3. And we looked at the time that it happened. We quickly summarized the duration of the storm, the time of the peak, 15-minute intensity, time of 30-minute intensity, as well as those peak intensities. So we could quickly kind of summarize and get a table of this. Here's an example of what that looked like. Here's some flooding in the town of Ruidoso. Um, and I can even take, in this case, there were 5 gauges that I pulled in the area. And so I pulled quickly made a table of the peak 15-minute intensities from all 5 of the gauges. And we can make plots like this. So what we're looking at is rainfall intensity is on the y-axis. The x's indicate anything that's below the threshold. The dashed line is the threshold, and the circle just shows that it's rainfall above our threshold. So getting from the raw data into a plot like this is relatively easy with some of the output from Flow Alert. Um, and it can be useful in unburned areas as well. Um, I'm not, I don't, that's not really the focus because, like I say, with unburned areas, we know that soil saturation is important, other things like that. But here's just an example recently from a hurricane that happened in the in Western North Carolina. Um, so this hurricane you can see in the photo, it's starting off the coast of Florida. It moves up the coast and it hits the Appalachian Mountains. So I just want to give you an approximate timeline of how this kind of played out and how I used Flow Alert to get some information about what was going on with the landslides here. So we knew there was a hurricane. Most of the rain was falling on September 26th, 27th. So I woke up on the morning of September 28th, and this was a Saturday. And I started looking for a rainfall total map around 10:30 in the morning because I really wanted to see where the maximum rainfall was falling in the Appalachians because we had a sense that where the maximum rainfall was going to be related to where most of the landslides would be. So I looked for about an hour, couldn't find anything, and so I finally decided, well, let me try to see if I could get the rainfall data with Flow Alert. So I drew a polygon. You can see this red polygon in the upper left. And it's a big area. So you can see the one side of that polygon is about 370 kilometers. Um, Within about 2 minutes of feeding this polygon into Flow Alert, it was able to identify the location of 542 gauges. And so then I wanted to pull the data and process it. So 11:35, I hit the button to pull and process 542 gauges. 1 minute later, I go upstairs and make a sandwich. And by about noon, I had plots, I had data for all of these rain gauges. So it didn't take super long time to get a lot of information. Um, and here's an example again of one of the plots that was, available. So I could look through 540 of these within about 25 minutes. And I can make these plots. Like here, for example, is the cumulative rainfall data from all the gauges. You actually can see one interesting fact from these is that several of them cut off before the end of the time that I queried. And the reason they're cutting off is because they're losing power. And so they're not actually able to report out the rain data. Um, but I was able to take that information because each gauge has a latitude and longitude. I could quickly make a plot with those. I was able to use the flow alert output to just quickly make a 24-hour rain rate. So this is rainfall in inches. I was interested in the total rainfall here. So we can see kind of with the red here, some of the hot spots of where we got the most rainfall, and then start to associate that with areas we might expect landslides. The last thing I want to show on this was one thing we were able to do to just get a snapshot of the rainfall intensity throughout this storm, this Hurricane Helene storm. So what you're looking at on the primary y-axis is the 60-minute rainfall intensity. And the secondary y-axis is cumulative precipitation, and that's from a single gauge, and that's that kind of blue shaded line. The intensity is the orange and gray filled lines. And what I've done there is I've taken the number of gauges, I eliminated many of them that seemed to be malfunctioning or maybe were just zeros. So we pared it down to about 384 gauges. And then for each 1 minute time slice, I just took the minimum and maximum 60-minute intensity. And so that's what's in those fill areas. And what's interesting is that the Orange area is the rain that happened before the hurricane even made landfall. And then the gray area is the continued rainfall intensity after that. And then there's a final black line that indicates again the mean intensity of all the gauges. And so I just wanted to demonstrate this to show some of the information we can use to get an idea of what's going on across a really large area. Obviously, we know there's a lot of variability, there's a lot of details, but this just kind of starts to give a snapshot of what's going on in the area. So, I just want to point out, I know a lot of people aren't in the US, and a lot of what I've said is US centric, but I did look at the Synoptic API that we use to kind of drive where we pull rainfall data from in Flow Alert. And they pull a lot of, they have a lot of gauges they pull from in Europe. And actually, interestingly, I recently got an email and they showed two new networks that they just started ingesting in Italy and England, over 7,000 meteorological stations here. So, this is something that could be used, outside of the US. So I just want to run through a handful of conclusions here. First, calculating rainfall intensity and gathering rainfall data is really a pretty easy concept. This is pretty straightforward. There's nothing extremely novel about it. But what I found is it takes some thought to develop a usable system to get information quickly. Um, and so, what's nice about this system we developed is Flowler allows us to look particularly at post-fire debris flows and try and estimate where they might be happening based on rainfall data. We can do this quickly through a dashboard. This is something that hopefully you can walk into the office and look at this dashboard while you're drinking your coffee in the morning and just get a sense of what's new in the area. Um, it also does a flow alert also does a lot of processing of rainfall data that allows us to quickly analyze data to just get a sense of what's above threshold, what's below the threshold, and helps us to decide should we change this as we get information from storms. Um, and flow alert can be used in unburned areas too, such as what we did with Hurricane Helene. It can tell us about the rain when there's a lot of flooding. So with that, I'll stop, wrap up, and I'll take any questions you guys might have.
Thank you, Francis, very much for that talk. And I would like to ask everyone, are there any questions related to this presentation? You mentioned already before, Francis, that this is a product which is geared to the US conditions, probably something, an in-house product from your institution. Is this available to other interested users?
It is, yeah. So Flow Alert is software that can be downloaded. It's written in Python. Um, it's freely available. It's on GitLab, a USGS specific GitLab, but it can be downloaded and used by anybody.